Erzähl mal, wie ist der Anschluss? No information. Ich habe das zweite Mal.
Okay, then let's continue with something that is supposed to give you a little bit of intuition. Can you please close the door? Thank you. Namely, the polar form of the Hello, can we start? The polar form of the Fourier series. So, what we've seen thus far, just to recapitulate that briefly, is that we can express a function in terms of the real Fourier series, as we've seen this morning already, in this form. And now we have also rewritten this, so we've found an equality to the so-called, as we just discussed like 10 minutes ago, complex, the so-called complex form of the Fourier series, which takes this form. Where the CK are defined once again in terms of the coefficients AK and BK. And remember, although I don't write them up right now, we have formulas for AK and BK in terms of the function f, right? So don't get confused there. So we know what these AK and BK are in numbers. For k equals 0 and 1/2 AK minus I BK for k larger than 0. And now the last thing to do is to again view the whole thing from a little bit of a different angle, from a different perspective, and also give some intuition to these complex coefficients, and also in a way to the re-coefficients, and to also get into the language how cognitive neuroscientists actually talk about Fourier transforms, because they like to talk about things like phase and amplitude. To get into this language, we will rewrite this again as the so-called polar form of the Fourier series, which takes the following form. So here we are without complex exponentials, and we only have a cosine term. So we have here the cosine with different amplitudes, which are now called d. And critically, we have here this phase term. So remember when we discussed the generalized cosine and sine functions in the very beginning, originally they had this phase term in there, and then I took it out because it was simpler, but we discussed that this is a means to shift functions, especially if phi k is positive to the right. Also, we discussed that it doesn't really make sense to shift the cosine much further than pi half, because then it's the sine, right? Pi half. Is it pi half or pi? Pi half, I think. So this is now our, this is a generalized cosine function, and of course there are new coefficients, and like the CK, these coefficients can be evaluated based on the AK and BK. So our D0 is A0, our DK is square root of AK and BK, and our phi k, so this phase, this phase or phase number is arctang, which is something like the inverse of the tangents function, which we also briefly discussed in the very beginning. So if you feel unsure about the arctang function, have a read again of the sets and function bit of the script. So it's the inverse of the tangent function of the ratio of bk and ak. So the point again is, if we know ak and bk, we can compute the dk in this representation. Yeah, so it's the same thing as for the complex one, now with these new formulas. Question is, of course, at least my question would be, where do these formulas come from and why does this hold? And this is what I want to go over now. So this is again, this now in the form more of a proof. So we know the result already. We know that the real Fourier series can be written as this, and we wonder why, which some people do. Good, then let's try to answer that. And again, this can be done with a little bit of help from some formulas, but then essentially just rewriting things. So what we need here to show that now the real Fourier series can be expressed as this. What we need are the cosine and sine properties. So these are things again that you can prove in your favorite analysis course. So these are also listed in the script, these equalities, but they are not proven because that's something left for the mathematicians. So if you put in a sum into the cosine, you can express this cosine of x plus y as the cosine of x times the cosine of y minus the sine of x times the sine of y. It's a basic functional property of the cosine. And then cosine and sine have certain symmetry properties, which you can essentially read off by looking at their graphs. So if you have, if you go to the left hand of the 0 on the x-axis, you will find that because essentially because cosine is and I think that's don't want to say something wrong. It's either even or odd. Does anyone here, the mathematicians, is this even or odd if they have this property?
I think it's even.
It's even. Okay. Because it's an even function, it is symmetric about the y-axis, so around 0. So this is this is the one symmetry property of the, or this is the symmetry property of the cosine, which defines it then, as we just heard, as an even function, but that's just a nomenclature. And the sine, which is not symmetric about 0, but inverse symmetric about 0, if you want, has this property. So if you go to the left, you add minus sine, which you can appreciate if you think that the sine starts there and then inverts itself after 0. So these are basic equalities for cosine and sine function that are typically taught in kind of undergraduate calculus, and we use them now. And we use them to first expand the polar form of the Fourier series to then see the equivalence, so basically to see that these equalities or definitions hold. Yeah, so this is also a typical math thing that you have some, like you've seen maybe now a couple of times, you have some preliminaries which you take as a given, because otherwise you would always do the Peter Scholze and start with what is counting. While we spend some time on this, we don't want to spend that much time on everything. So we start with some preliminaries which we don't question, but assume that everybody's happy with them, and then we use them. So let's use them. So we start by expanding the polar form. So this is our polar form, as we just said. it is. And then the first thing that we can use is to basically split the cosine according to this equality, so that we get our sine back, because we want to somehow, of course, relate it to the real Fourier series where we had the cosine and the sine. So we can write this term as dk, and now we apply this formula there. So we have cos k omega 0 x times cos minus phi k. So just realize that we have a plus here, so we need to take care that we had a minus there. Minus sine k omega 0 x sine minus phi k. And then we can use these symmetry properties to rewrite cos minus phi k as cos phi k, because that's also established. And we can rewrite rewrite sine minus phi k in terms of minus sine phi k. So we get a plus here because we get a minus in front of the last term. So we get sin k omega 0 sin phi k. Yeah, so far happy? So this is just following from these equalities that I just pulled out of the head like a minute ago. But then that's okay. And then we can expand the what I'm missing here is brackets. There, of course, I need brackets. So we now get fairly close to our real Fourier series. Actually, I'm also switching. That's better. I'm switching the cosine and sine terms. So just change the order of multiplication, because then it's easier to see. So now we are essentially quite close to our real form. So we have now, if we call this thing AK and this thing BK and A0 D0, then we are back at our real Fourier series. Yeah, so that's the same thing, and this just follows. Of course, we could have also started here and defined things like this. It all just follows from the properties of the cosine and sine function. So we now have AK. So we have essentially equalities that relate our dk and AK and BK coefficients, and they take the following forms that I'm just writing out here, like this. And now we want to actually solve these for phi k, because we want in the end to get here. And this is then just a little bit trickery to basically get, so we have if you want, we have a system of two nonlinear equations which we now want to solve for phi k and dk, and for systems of linear equations there are ways, or there are recipes to do that. For systems of nonlinear equations, it's just, you need very good intuition and basically there are no real recipes. So it's I would say, I mean, you can also establish recipes there, but often it's just fairly ad hoc how it's done. And this ad hoc way, this is also now used here. So to basically get to the phi k, what we can do is we can divide bk by ak, which from this is dk sin phi k divided by dk cos phi k, which then gets rid of the dk, which is good. So we isolate our phi. And this, in terms of also the dividing sign of something by the cos of the same thing is the same as forming the tangents of this thing, which is the definition of the tangents function. And then if bk ak is in minus pi half to pi half, one can invert the tangents function. So these arcus, arc cos and arc sine and arc tangents function, they are essentially the inverse function of the cosine, sine, and tangents functions. But these functions are not really invertible because they repeat themselves and so on. So you have so they are not bijective. So you can only form the inverse function over certain intervals, and this is why they're called arcus tangents and so on. And they're not just called inverse of the tangents. So sometimes these are also written as tang to the power of minus 1, but that's a little bit confusing because it's not really an inverse function, because it's only defined on this interval. But on this interval, then phi k is given by the inverse of the tangents function on this interval of bk ak. Yeah, so we form, basically we get the phi k out of here by applying the inverse of the tangents function to the whole thing. So we have inverse of bk ak. So this is then where this first formula comes from. And the second form for the dk follows, there's one magic formula that I haven't introduced. There's another magic formula of cosine and sine, which is the following: cos x, so cosine square plus sine square equals 1. Again, something that is established in undergraduate calculus or undergraduate statistics. That's a question. Sorry.
Shouldn't we exclude the case of AK being 0 in this case?
The AK what?
Yeah, if you do like division, BK AK should be 0.
That's true. And I actually wonder whether it's the open interval. I think it's actually the open interval.
But on your script, I think it's close.
Yeah, but that's just my script. Yeah, so if AK is 0, this is not defined. So let's hope that AK is never 0. The other formula for the dk comes about also with a little bit of magic, that if one squares the ak and the bk in this form, then one gets dk cos phi k squared plus dk sine phi k squared, and then one can take the dk squared out of it and has this cos phi k squared plus sine phi k squared, and I just established that this is 1, so we have d square k equals a square k plus b square k, so then we get dk equals square root ak plus bk. So these proofs or verifications or whatever, they are not really nice because they are fairly ad hoc, so it's not that you can really learn something from them, only in terms of if you're ever in a situation where you need to solve something like this, you might remember how it was done in these circumstances, but it's not a general rule or something, so it's not so these kind of proofs or derivations I don't really like. If they're just kind of like Pappbecher, you can just use them once and then you can throw them away. But anyway, they show how you can get to these formulas and how you get from what we've done before, from the real Fourier series to the polar form of the Fourier series. So we have now 3 ways to look at the Fourier series, namely the real Fourier series, the complex Fourier series, and the polar Fourier series. And now finally, with the polar Fourier series, and kind of to finish this whole business of Fourier series representation, I want to discuss kind of a graphical perspective on these coefficients, which for some reason is popular in neuroscience. I don't think, well, it adds a little bit in terms of perspective, but it doesn't add that much. But other questions so far? No, good. This was also quite easy. It's just a third form that you come across quite often. It's called polar because it's also, of course, related to polar coordinates, as we will see in a second, which are ways to express two-dimensional vectors in the plane, not in terms of the location where they are, but in terms of the length of the vector from the origin and the angle, as we will see in a second. So how do we start with that? So yeah, I think the biggest thing that one always wonders about, or at least I wondered about, is the thing with the complex numbers that one gets out of Fourier transforms. So next week will be Fourier transforms. So please be prepared for Fourier transforms. So maybe go over the stuff in advance. That would be good, like always. And in Fourier transforms, one usually gets complex coefficients out of them. So let's start again with our complex coefficients, which we had seen are given by this. So depending on k essentially, well, then we also would need a plus minus. Yeah, I mean, it's let's do it properly. It was plus if, am I doing it the right way? Plus and minus, no, then it's minus. It's minus if k is larger than 0. Maybe let's focus on them. It doesn't really matter. We can, Jesus, let's do all of them. A minus k, I just wrote them up so many times already. And a0 for k equals 0. So, thing is, if you're given now the ck, not the bk and ak. So remember, we started out with the real Fourier series, evaluated the ak and bk, and then we went to the complex Fourier series and then to the polar series. Now we in kind of in pre-knowledge, no, in kind of in preparation for the Fourier transform business, we assume that we're actually given the CK. Now the CK have these forms, AK minus IBK, so they are complex numbers, and last week we discussed that complex numbers have real and imaginary terms, right? So does anyone remember, if you have this complex number, what is the real part of the complex number C? A, exactly, and what is the imaginary part? B, exactly. So if we now evaluate the real part of one of these CKs, then we get what? AK, essentially, but we have 1/2 in front of it. This is just a little bit annoying, and one can add. There are actually ways also to get rid of this 1/2, but we keep it here. And the same way, the imaginary part of this CK would be plus minus 1/2 BK. Yeah. So essentially, we now trying to make sense of the complex coefficients that we are given. Yeah? CK given. Then we can evaluate the complex, the real or the imaginary part of this complex number, and then we know we have our AK and BK. So we can represent this, as we also did last time briefly, when we talked about complex numbers. We can represent this in a 2D coordinate system, where we either call the axis x1 and x2, or maybe even more familiar for you, x and y. Yeah, and represent our complex numbers or two-dimensional vectors in that. Yeah, so we can now also call these axes the real and the imaginary axis. This is completely equivalent because we have this bijective mapping. Imaginary. And we can represent a complex number CK as a point in this plane. If we use as its coordinates the real part and the imaginary part, which are, of course, if we, instead of representing it in a real and imaginary plane, but instead of in a x1 and x2 or x and y coordinate system, are just the coordinates 1/2 AK and 1/2 BK. Yeah. So this is equivalent. We have a two-dimensional entity. The two-dimensional entity are either the coefficients AK and BK times 1/2, or they are the real and the imaginary part of our complex number CK. Yeah? So a complex number is a two-dimensional entity because it has a real and imaginary part. Good. Now we can, if we have this thing in the two-dimensional plane, we can also, of course, view this as a vector if we essentially draw an arrow from the origin to this point. Yeah? So this is still our number here. So for example, to make this now really concrete, let's say this is 1, 2. Yeah, so our real part is 1, our imaginary part is 2, for example. Or because it looks more like this, both are 1. Doesn't really matter, but it's two numbers that you can plot in a plane. And somehow we need to get rid of this 1/2, but it also doesn't really matter. We can also deal with the 1/2. Then the length of this vector is, if you remember some high school trigonometry, is given by the Pythagorean Theorem, which if we let's call this, to confuse you, let's call this x and let's call this a and b, because it was always called a and b, and this is c. So what is the length of c from undergraduate, from high school? The length of this? Exactly. So that's Pythagorean theorem. And now, of course, our a and b are here 1/2 ak and 1/2 bk. So I really want to get rid of this 1/2 now. Let's call this 2 ck, so that we get rid of this 1/2. So then we have here ak and bk. The other way around, sorry. The imaginary is bk and the real part is ak. And then, based on the Pythagorean theorem, the length here is square root a square k plus b square k, which is our dk. Yeah. What is this supposed to mean? Well, this is supposed to mean that if you are given this complex coefficient in the exponential, in the complex representation of the Fourier series, then if you evaluate the real and the imaginary part of this complex number, and you take the square of these real and imaginary parts, sum them, and take the square root of it, then you get to the amplitude of the cosine term in the polar form. Yeah, and we worry about the 1/2 factor at a later time point. So what this is supposed to show you is, if you have ck, which is a complex number, you take the real and the imaginary part of this complex number, and then you square both of them, add them, and take the square root. Then you have an amplitude, in the sense that it's the amplitude coefficient in the polar form of the Fourier series. Yeah, and somewhere in there is a 1/2 factor that is a little bit annoying, but of course it's just a conversion factor, which then means that the amplitude is 1/4, 1/2 or something. Yeah. So that's one thing. And the other thing is, of course, the angle. So this angle can be computed. So this, we call it now already phi k. This can be computed as arctang bk divided by ak, which is also something that you played with in school. So that's that might be surprising now, but it's essentially just from doing the trigonometry of rectangular triangles that this angle. So you might remember that Gegenkathete divided by Ankathete is tangents of this angle, and then you get to the angle by computing the arctang. So that means, again, if you are given this ck, you evaluate the real and the imaginary part, and then you evaluate the arctang of the ratio of bk and ak, then you get the phase information in the polar form. Yeah? So you get to this phase term. And so this is what, so phase is often, if we are now then later on talk about frequency spectra, phase is often discarded. So if you do the Fourier transform, you get these complex coefficients. What neuroscientists typically do is to get these complex numbers and square them, add them, and take the square root and maybe call that energy or whatever, and then plot this. So they throw away the phase information and look at the amplitudes of given frequencies. And this, if you look into reviews in cognitive neuroscience, it's not really explained where this is coming from. So in a way, it's what they sometimes show are these plots here. But of course, if you are not familiar with the polar form of the Fourier series, then this doesn't really make sense. Yeah, but this is essentially then what I wanted to say about Fourier series. So remember how the whole thing works from the very beginning. So we are given a function. So we don't have data yet. We're still waiting to talk about data. We're still dealing with analytical functions. We know that this function is periodic, or we can form protracted functions, and we know that it fulfills these other Dirichlet coefficients, Dirichlet conditions. Then we can compute the real Fourier series coefficients based on the integrals that we did in this 1 hour, and then, because we have nothing else to do, we can convert these coefficients into the coefficients of the complex Fourier series, or we convert them into the coefficients of the polar form series, and then we can also look how we can convert the complex coefficients into the polar form coefficients, or the polar form coefficients into the real Fourier series. So it's always the same thing that we're looking at, just expressed in 3 different ways, where the cosine sine should be closest to intuition. As you remember, in the beginning we did these sums where you could see that if we add multiple cosine and sines together, then we get interesting functions. More technically minded, the complex exponential, and potentially more intuitive again, the polar form. Yeah, and this is actually where I want to stop talking on this for today. So are there questions about this whole complex of Fourier series?
I just have a question on that last part, because when we were drawing the vector, we said that the length of the vector is dk, but in this example, to get rid of the 1/2 ak, 1/2 bk, we said, so we have 2 ck. So I wanted to ask if you wanted the length of ck.
Yeah, so you're really worried about the 1/2 factor. So let's do it. Yeah, I mean it's fair enough. So it's let's do it then properly. So we have ck. So the real part of ck is 1/2 ak, and we assume that we have a positive k here. So the imaginary part is, this has to do actually with this, how one normalizes the space frequency. And then there are ways to get rid of the 1/2, but then one has other 1/2 somewhere else, so it's more or less helpful. We have them now here, bk. So if we plot ck, then we have 1/2 ak, 1/2 bk. So that's our point here. So then we would have to do 1/2 ak plus 1/2. So if we now want to compute the length of this ck vector, bk, we need to square them and take the square root. So we get 1/4 ak square plus, so we get 1/4 ak square plus bk square. So let's finish this. Everybody happy? Janis, I'm doing live calculations, so if it comes if in doubt, or anyone else, please shout.
No, I cannot have it. Shouldn't it be 1/2? No.
Yeah, this is what you mean. Okay. Thanks. And then we have 1/2 a square plus b square. Okay. So then the length here is actually 1/2 dk.
Yeah.
So now I actually took care of this 1/2.
Yes. Thank you. No, I was just wondering, so if we wanted to put all that into the polar form, would we have to use the 1/2 dk? Or would we, like, what,
no, then you would...
from putting in there dk, would that be 2ck and we would have to divide that by 2?
I didn't quite follow the last thing, but you would have to, if you compute it, so if you assume, of course, you always, this is a little bit, if one does the whole thing with variables, one sometimes has the feeling that these are not numbers, but of course these are numbers. So let's say that ck is something like 2 plus 3i. Then we here have 1/2 times 2, and here we have 1/2 times 3. And then we can compute this, but this is then 1/2 dk. So if we want the dk, we have to multiply it by 2. So this is what I meant earlier, that there's this factor 1/2 somewhere, which is, but this just scales the coefficients with respect to each other, always with a constant factor. So the meat of the formula is in other parts.
I don't know if this is relevant, but
Yes.
is real and imaginary always perpendicular, like linear system, 90 degree? Because if, like, are there cases when it is not, or it's not important?
That's not actually. You mean why we draw it in the real in this system? No, this just comes. So it doesn't mean that real and imaginary are orthogonal. It means that. So yeah, I mean, so that I'm not quite sure what you mean. But so one question could be whether the real parts and the imaginary parts of complex numbers co-vary, and that's not really that meaningful because they just span the complex numbers are just spanned by r squared, right? So you can, for A, you can put in all real numbers, and for B, you can put in all real numbers. So in this sense, so if you have all real numbers here and all real numbers here, in this sense, they are by design orthogonal because you can so all of them are allowed. And then this way of representing a point here by the real and the imaginary part of a complex number. This is just this bijective mapping that I discussed last week, where essentially you just have these two things. You have the real part and the imaginary part, and they can be anything. This is not stochastic or anything, so there are no covariations between the A and B. Of course, if you evaluate certain data sets or whatever, then it can be that for some reason that the real part and the imaginary part covary, can be. But by design, the real and the imaginary part of a complex number have no covariation. It's not even a meaningful concept. And even orthogonality is... It's a little bit tricky as a concept here, because one would have to, so orthogonality of course would be defined for two-dimensional entities, and this would be then, it's not really meaningful. So one can be mathematically creative and invent something like orthogonality, and I guess somebody has invented it, because mathematicians also need to pay the rent. So somebody has definitely invented something about orthogonality and complex numbers, but it's here what I mean is just that complex numbers and two-dimensional real vectors are the same thing and can be always transferred into one another. Yeah? Good. Then I hope everyone is so far happy with Fourier series, and then next week we use all this knowledge to be able to talk about Fourier transforms. First the analytic version, but then, and this is actually more important, the discrete version, where we finally actually put in some data and leave the pure mathematical realm and actually deal with data on which we can compute. Yeah? Good. So then let's have a break and let's start again at 10.